Okay, welcome back. We are going to continue our discussion of chemical equilibria. So I hope that you were sufficiently fooled in the last video that I posted. And I hope that you found this video because we are actually doing some work today, even though we started out with a little fun. Okay, so happy April Fools, everybody. I hope that you guys come up with some interesting pranks to pull on you and your isolated / quarantine family members. Nothing like a little family togetherness, right? Okay, let's continue with this idea of the units that are involved with the equilibrium constant. Okay, so yeah, let's talk about this. Units for Kc and Kp. It's confusing, but we can't ignore it any longer. Okay, so the units for Kc and Kp are somewhat confusing. Oh, sorry, I'm gonna change something around. It might make a lot of noise. Just moving my tablet around. Okay. So in practice, Kc and Kp, these two equilibria terms, are standardized against 1 mole per liter and 1 atmosphere. Okay. So the mole per liter is the standardization for Kc, and the atmosphere is the standardization for Kp. Okay. Okay. So they are standardized against 1 molar and 1 atmosphere. Okay. So basically, they're always being divided by 1 molar and 1 atmosphere. So as long as we use units of molarity for Kc and atmosphere for Kp, we can completely disregard the units of Kc and Kp. I know what you're thinking. Dr. McDonald is saying that we can disregard units? This must be a new April Fool's joke. Unfortunately, or maybe fortunately, depending. Actually, it is fortunate because the units of Kc and Kp get really confusing. So this is not an April Fool's joke, I promise. You can disregard the units of Kc and Kp as long as you make sure that you always use units of molarity for Kc and you always use units of atmospheres for Kp. As long as you do those things, you can completely disregard those units. Okay? You're welcome. Happy birthday. Maybe it's somebody's birthday out there. Actually, if it is your birthday, you should email me and let me know, because that would be pretty cool if I just kind of like guessed your birthday there. It's too bad that I can't say this in the classroom, right? This would be a perfect opportunity to be like, hey, everybody with a birthday today, raise your hand. Yeah, nobody raised their hand here because it's not my birthday. So, okay, next. So that's the units of Kc and Kp. You can basically disregard them, but you have to make sure to use units of molarity and atmospheres. Okay, next we want to talk about something called heterogeneous equilibria. Okay. Heterogeneous equilibria are reactions that involve pure solids and liquids. Okay, so they include pure solids or liquids. For example, okay, I'll give you an example here of a heterogeneous equilibrium. If we react two carbon monoxide gas molecules to form carbon dioxide gas and carbon solid. Okay, the Kc for this, we would make it as CO2 times carbon solid divided by CO squared. Is this what we would do here? Nope, nope, nope. This is not correct. Mostly because how do you define the molarity of a solid? The answer is you can't. So Kc in this case is actually just CO2 divided by carbon monoxide. Okay, we completely disregard the solid. And as a matter of fact, we assume that solids have a constant concentration. And this kind of makes sense, right? If you have some space that's filled up with a solid, you're not going to get any more solid within that space. So the amount of moles per liter remains completely constant. Since the molarity of the solid remains constant, they are not included in the equilibrium constant expression. Okay, and so we just have Kc is equal to CO2 over CO squared. Okay, so anytime you see a solid in a reaction, do not include it in the equilibrium constant. What about liquids? If we have a reaction between CO2 gas and H2O liquid to form H plus aqueous and HCO3 minus aqueous, this has a pure liquid as part of the reaction. Okay, it can't happen without that pure liquid. And the way that we would form this Kc is by having the products over the reactants. However, just as in the case with the solids, the liquid is constant. Okay, the liquid concentration is constant. So we do not include it in the equilibrium constant expression. We just include the pieces that are non-liquid. HCO3 minus divided by concentration of CO2. Okay, so this is the equilibrium constant expression. There is no concentration of water. So pure liquids and solids, not included in Kc or Kp. Okay, don't include them in those expressions. Okay. Okay. So we're going to do a little quiz. Which reaction among the ones that are following has Kp equal to Kc? Is it A, B, C? A is 2 times sodium oxide reacting with carbon dioxide to form sodium carbonate. Okay. The next is iron iron oxide reacting with carbon monoxide to form iron, solid iron, and carbon dioxide. And the third reaction here is ammonium nitrate reacting or decomposing to form N2O and 2 waters. Oops, that's not a liquid, that's a gas. Okay. Now remember, Kp is equal to Kc times RT raised to the delta N. Okay? So you need to ask yourself, or try to figure out for yourself, in which case will I have Kp equal to Kc? What is the necessary condition for Kp therefore to equal Kc, if this is the definition of their equality? Well, we have two parts of this. Okay, we have this Kc here, and we have this term RT raised to the delta N. Now we can get this whole term here to equal 1, and therefore Kp would equal Kc. We can get this whole thing to equal 1 if and only if delta N is equal to 0. Okay, so that's how we can get it equal. That's how we can get Kp equal to Kc. If the change in the number of moles is 0, then Kp is equal to Kc. All right. So first of all, let's look at A. Delta N in this case is equal to the sum of the products minus the sum N minus the sum of the reactants. Okay. So that's this one would be product is 2 plus 1 minus 2 plus 2 equals -1. So the change in N is -1. That can't be Kp equal to Kc. Let's do B. Delta N is equal to, in this case it goes from products 2 plus 3 minus 1 plus 3 is equal to +1. Okay, so this also has a non-zero delta N. Let's look at C. C is delta N equal 2 plus 1 minus 1 is equal to +2. Okay, so it turns out that none of these have Kp equal to Kc. The only way you can get Kp equal to Kc is if you have a delta N that is equal to 0. Okay, so all three of these cases, Kp does not equal Kc. Okay, and there are some examples in the book. Basically, anytime you have a reaction that has the same number of moles in as the same number of moles out, you have Kp equal to Kc. Okay, let's go through the process of figuring out exactly how to calculate Kc. Okay. Okay. Say we're given some reaction. The reaction of hydrogen gas with iodine gas to produce hydroiodic acid gas. Okay. This is at equilibrium at 445 degrees Celsius. Okay, and the concentrations that we read for these are hydrogen gas equal to 0.11 molar, iodine gas equal to 0.11 molar, and HI equal to 0.78 molar. Okay, so in this case, we just plug them into our Kc equation, which we can find just by looking at the equation here. Okay, so that we have products HI concentration divided by H squared, or excuse me, hydrogen concentration and iodine concentration multiplied together. Okay, so now we just plug in the values. So we have HI concentration 0.78 squared divided by 0.11 times 0.11, and that gives us a value of 5.0 times 10 to the 1, okay, which equals 50. So the Kc for this reaction is 50. Now, Kc is always constant at constant temperature, okay, regardless of the initial concentrations of the reactants. Okay, so it is always constant, no matter what the concentrations are. When you start at equilibrium, Kc will always be constant with constant T. Okay, so if we have some generalized reaction, a gas is decomposing into 2B gas, okay, at 25 degrees C, we have A init, that's the initial concentration, is equal to 1.00 molar, and we have B init equal to 0.75 molar. Oops, sorry, this is not B init, this is A equilibrium. Okay, so that's A at equilibrium. B init, the initial concentration of B, is 0.00 molar. We haven't made any yet. Okay, so then we have B equilibrium is equal to what? Okay, can we solve for this? The answer is to use something called an ICE table. And ICE stands for initial change equilibrium. Okay, initial change equilibrium is an ICE table. So the way that we form these is we write out ICE going down like that. So we have initial change equilibrium, and then we write out the concentrations for everything within our reaction, which is just A and B. So initially we have a concentration for A of 1.00 molar, and we have an initial concentration of B of 0.00 molar. We have a change in A going between 1 and 0.75 of negative 0.25. Okay, and in the case of B, we must have a change in B that is equal to 2 times the concentration of A. Okay, and this would be positive increase. So 2 times the change in A based on the stoichiometry of the problem. Every A that we decompose, we must make 2B. So this must be 2 times 0.25 molar. Okay, then we have equilibrium, which is 1.00 minus 0.25, and this is 0.00 plus 2 times 0.25. Okay, so at equilibrium, you just add these two values together. Okay, and then we have the equilibrium constant expression. Kc is equal to B squared over A is equal to 0.50 squared over 0.75 is equal to 0.33. So that's the equilibrium constant. Now, we were just asked what the value of B at the equilibrium was, and this gives us the value of B at equilibrium, 2 times the change in A. Okay, so B equilibrium is given there, and it equals to 0.50 molar. Okay, so we have Kc, and we have the concentration of B at the equilibrium. So we've solved the problem using what's called an ice table. Now, ice tables can be a lot more complicated than what I've just drawn. This was a very simple explanation. Okay, so let's do another example. Let's do one more example here. Let's react carbon monoxide with hydrogen gas to form methanol. Okay, let's do this at a temperature equal to 780 degrees Celsius. We have an initial concentration of CO equal to 0.500 molar, an initial concentration of hydrogen equal to 1.00 molar, and a concentration of carbon monoxide at equilibrium of 0.15 molar. Okay, what is K in this reaction? Let's write out our ice table again. ICE, and sometimes it's useful to write a little line here and then show the product or the reactants, concentrations of the reactants, and then separate out the reactants from the products with a line again. And we have methanol here. Okay. If we look at the initial concentration of CO, it's 0.500 molar, H2 is 1.00 molar, and methanol is 0.00 molar. Okay. In this case, we have 500 molar minus the amount that is left at equilibrium, which is 0.15, and the difference between those two is negative 0.35. So this decreases by 0.35. And then we have, in this case, we have to use up 2 times that same amount because of the stoichiometry of the problem for hydrogen. Okay, so we have to use up 2 times the amount that we use of CO stoichiometrically, so we must have 2 times 0.35. So this must be 0.70. Okay, and in this case, stoichiometrically, it's 1-to-1 with methanol and carbon monoxide. So we must form the same number of moles as we used up from CO of methanol. So that means that we form 0.35 moles of methanol. At equilibrium, we just add these together and we get 0.15. This agrees with what we have initially, what we were given for the problem up here for the equilibrium concentration of carbon monoxide, so that's good. We can calculate the equilibrium concentration of hydrogen. Oh, sorry, that's not right. That's right. And we can calculate also the equilibrium concentration of methanol. Now that we know all of the equilibria concentrations, we can plug them into Kc is equal to CH3OH divided by CO times H2 squared. If you look at the stoichiometry, that's why there's a square there. And now we just plug in the numbers. So we have on top 0.35 divided by carbon monoxide 0.15 multiplied by hydrogen gas concentration 0.30 squared, and we end up with a Kc value of 26, or 2.6 times 10 to the 1. Okay, so that's how you calculate Kc. Again, it can get much more complicated than this. This was kind of a simple example, but we will get into more difficult examples later on. Okay, so that'll be it for part 1. I'll see you back here for part 2.